Okay, good afternoon and welcome to today's lunchtime lecture. I'm Paul McMillan. I'm from the chemistry department and I'm a member of the lunchtime lecture committee, and I'm chairing the lecture today. Before we begin, could you please make sure that your mobile telephones are switched off? Including the speaker. So our speaker today is Professor Brad Karp from the Department of Computer Science, and he's going to be speaking about something very topical about our use of the internet and issues of privacy and security. So, Brad.
Thank you very much, and thank you all for taking time to come today. I think it's pretty safe to say that all of us use web applications today. I mean, there might be a few holdouts left in the room, but almost everybody is using the web for something or other. And this leads, in particular, in light of recent events that have come to light in the press about various privacy breaches, to concerns about your data, your sensitive data, and how well it's protected, how well your privacy is preserved in web applications. And so my talk today sort of has two parts. What I'll eventually get to in my talk is to talk about how today's architecture of the web, and by that I mean the way the system as a whole was conceived from the outset, sometimes can cause a choice between privacy and functionality, between using something you want to use and your privacy. And I'll talk about how we can try to make it so people don't have to give up privacy to get functionality that they want. But before that, I'm going to sort of give you an overview of the menagerie of web security, because it's such a broad and fun topic and hard topic that it might be good to get some grounding before we start. So I've been using the web since about 1995. I remember somebody showed it to me when I was a graduate student, and I said, oh yeah, this thing will never take off. I'm here to do computer science research. This is a terrible idea. There's nothing interesting about this. That's why we needed a physicist to come up with the web. So originally, early websites were static documents. Right? It meant that somebody could take their record collection, or maybe it was CDs by the 90s, and make a web page that had their comments on their record collection. And the thing that was sort of cool about it was, for enthusiasts, they could make links to other people's websites and said, well, this guy really likes this record too, and then you could click on the link and go visit the other site. So basically, the web browser in that era, in the 90s, was sort of taking a document and displaying it for you, and that was it. Pretty boring. But today, we use web applications, right? You do banking, you transfer money using your web browser, you send and read email using your web browser, and so on. And what's interesting about this is the browser has evolved far, far, far beyond just displaying documents. Now, when you visit a website, the website has a program on it written by God knows who, which we'll come to a little bit later. And your browser just retrieves it and runs it when you visit the website. So I don't think I need to tell you that a lot of the web apps you use handle sensitive data, right? People express political views. Even which sites you visit might reveal your political views, right? Even if you don't interact with those sites particularly much. We manage finances. A lot of websites know where you are or where you're going to be. Right? So a lot of this information you might not want to fall into the wrong hands. So given that there's a lot of sensitive information floating around in web applications, what do we do? Well, the first thing most people think of is, oh, it's the internet. The internet is the problem. My sensitive information is going to be crossing this huge infrastructure that spans many continents, and I don't know who's going to be looking at it. And so people immediately think that that's the problem they need to solve, and they're sort of partly right. The part I like about this is what we'll call as a goal confidentiality, which means that our goal is going to be that only authorized parties can obtain the user's sensitive information. So if you're doing online banking with bank.com, and that's you on your laptop with the unknown big internet in between, then the authorized parties in this case will be the user on the laptop and the server or the operators of the server, and no one else. Nobody else should see your banking data or your login credentials for the bank. And so when you want to make it so that bad guys on the internet can't look at your sensitive information in transit, we turn to cryptography, also called encryption, which works pretty well. If there's a bad guy listening in the middle of the internet and you're using encryption properly, then they won't be able to understand what's going by. So this talk's finished. Encryption solves the problem. Are we really done? With one thing you might get out of this lecture today is what I'll call system security thinking, how people who are researchers in computer system security, as I am, approach questions of, have we achieved a goal in a system? So one thing is that security is a negative goal. If I build a system and I want to convince you that it has a security property, what I'm really saying is that system will never do something. Right? If I told you it did do something, maybe you could think about how to test. If I told you it will never do something, well, how would you begin? Right? In every situation of use for the entire system, would it ever happen that it would, say, reveal the sensitive information? Well, the first thing you would need to think about then is what's inside the web application system as a whole. Okay? And so this is the scary part of the talk. There are many, many things in the web application ecosystem, everything from human users, be very afraid, to hardware, be equally afraid, as it turns out. And I'm going to talk to you very rapidly just to give you a flavor of the landscape of the kinds of risks that exist at every layer of this web system as a whole. Okay, just to sort of level set. And I should say, I did not discover these flaws. There's a rich community of researchers who have discovered the things that I'm going to be talking about. I should also say most of these are long known, and most of them are pretty well solved by now, but not all. So let's talk about user behavior, the user. So you all know that you log into websites using your username and a password. Right? This is how you prove that you are who you say you are. How do you know you're talking to the right website? This is something that you as a user have to decide. How many of you have heard of phishing before with a PH? Okay, good. So phishing is where you receive an email that says it's from PayPal. It's not from PayPal. It's from somebody who wants your PayPal credentials, but they make the email look like it's from PayPal. There's a link in the email which you click through, and you get a website that pretty much looks like PayPal. So this is trying to trick the user into believing that they're on a site that they're not. If you type your username and password, it's whoever runs that non-PayPal site that gets your username and password. That's just the basic. But let's talk about an interesting twist on confusing the user. How many of you have smartphones? Great. So in iOS, for Apple smartphones, because the screen is so small, one of the things that Apple did to try to make better use of this small screen is let you scroll the web page and make the URL bar disappear off the top so that more of your screen could be used for viewing the page. This is great for attackers, right? Because what it means is that they can construct a page that has an image of a URL bar of the site they want to pretend to be, and then include a JavaScript program that begins the page when it appears by scrolling up a little bit so that the real URL bar is hidden and all you see is the image of a URL bar that's visually indistinguishable. So what I've shown you from some work from Dan Bonet and his students at Stanford is on the left, this is the actual page that the bad guy created. Badguy.com is the real name. And they want you to think you're on Google. And then they create the page in such a way that when it first displays, the JavaScript in the page makes the page scroll up a little bit so that all you see is the lower one, which is just an image they put on their site. Now you think you're browsing Google. Pretty nasty. Let's go down another layer, the web architecture. What do I mean by the web architecture? What I mean is the conception in the designers of the web's heads about how they thought the web would work. What module is allowed to do what? Okay. So let's talk about a problem there and an attack on the web architecture. How many of you have heard of cross-site request forgery before? Not so many. Okay. So you've got your bank and your laptop. You want to use it across the internet. You log in. These are not my actual credentials. Brad and Woot as my password. And what actually happens on the web is that because it's inconvenient for me to type my username and password, we have a way for your browser to sort of remember how to prove to the web server that you really are you. And what I mean by that is when the web server responds, it sends you something called a cookie, saying for the site bank.com, here's a huge number that I picked randomly. And by the way, all of this is using encryption, is using cryptography, so no eavesdroppers can hear any of this in either direction. And then what your browser will do is say, okay, great, I'll remember that for bank.com, this random big number is my identity. And then the next time you want to do something on bank.com, what the browser will do without asking you is when you click on a link on bank.com, the browser will find that cookie, which it's remembered from before, and enclose it in your request sent to the bank. And that request might be, say, a transfer to an account number and an amount. And I'm doing this. I'm sitting in front of my browser, so this is great. And then the bank.com server says, oh, I recognize that cookie. I gave it to this user. I know he really is the right user. OK. And then the server says, OK, one of the most pleasing and perhaps frightening at the same time messages in all of computing. So here's how cross-site request forgery actually works. Everybody knows that what the internet's real purpose is looking at images of cats. So I want to use your bank account, so what I do is put up a cat image website and get you to browse it. So the bad guy puts up cattopia.org. Then you get a web page, you see lots of images of cats, and there's one image that's pretty small that has a link, because you can make images be attached to links on the web. That's the whole point. And what that link does is it has a link to a bank.com URL. And it's the URL to make a transfer to an account number that the guy who runs cattopia.org has. Now, this shouldn't work, because normally you'd need to log in with your username and password. But unfortunately, what the browser does in this case is it says, oh, this is a request for bank.com. Do I have a cookie for bank.com? Yes. I'll enclose it. And now the website thinks that it was really from the legitimate user and makes the transfer. Okay, so that's cross-site request forgery. Going further down the stack, the next thing that's hard to get right, notoriously hard to get right, is how we use cryptography. So I don't mean how you program cryptography. I mean the conception, the design of how you employ cryptography in the system. Even that is very hard to get right. So I'm going to tell you about an attack called the crime attack. It turns out most of the crypto attacks have very sort of cute names. I don't know why that is. Crime, time, beast. So this is for compression ratio info leak made easy. Here's the rough plan. So first, background. You've probably heard of compression before. You have a big file, you want to make it smaller. What compression does is it finds repeating patterns in the file you started with and represents them more compactly. And then you get a smaller file. You give the compressed file to someone, they can decompress it and get the original back. So now we know about encryption. We've already talked about that. Let's say your web browser wants to both compress and encrypt something that it sends to a server. Which order should you do the two operations in? If you ask any computer science undergraduate, they will, in some sense, correctly tell you, oh, you should definitely compress first and then encrypt, because encryption has the property that it eliminates patterns in the input so that the output cannot be matched to the original input. It obfuscates. So compression doesn't work well after you do encryption. Right? So compress first, you'll make it nice and small, and then encrypt. Well, yes, but this is a terrible idea if you're sending web requests with cookies. I'm not going to go into the full details, but the rough intuition goes like this. What happens when you compress and then encrypt for a request with a cookie like that bank transfer is that you entangle what the length of the encrypted request is with what the value of the request before encryption was. So if an attacker can sort of do cross-site request forgery and try lots of different request strings and get your browser to issue them, he can try to inject patterns into his request and see if they cause compression to improve on the encrypted output, because he injected a pattern that matched part of your cookie, and then things got smaller. And so just by seeing that the encrypted request, which he can't understand, got smaller, he can deduce, I know a couple bytes of your cookie now. And he can iterate that. The fix, which is widely adopted, is don't compress web requests. They're small anyway. The browser vendors have learned that lesson now. Another example is, unfortunately, all of this stuff I've been talking to you about so far is just conceptions in people's heads and on whiteboards. But then you've got to implement it all as software. Millions and millions of lines of software written by humans, or as I like to call them as a programmer myself, primates. So an example of getting things wrong in software is the now classic go-to-fail, which happened just a couple of years ago. This is an error in the programming of SSL, which is the encryption library for encrypting things and making sure you're talking to the server you think you are on the web. So, so go-to-fail goes like this. You don't need to be a programmer. You can think about it if you are. but that's the actual program for SSL in a revision of SSL as implemented by Apple. And the yellow highlighted line is a duplicate line that should not be there. A simple cut and paste error to make. The consequence of this, which I'm not going to go through in detail in the program code, is that when this bug was out there in the iPhone's operating system and on Apple laptops' operating systems, all of these web browsers that these users were using would just not check at all that supposedly secure web servers were the servers that they claimed to be. There was just no check. They would just credulously report that it was the real server. So if an attacker came in and tried to impersonate, they could without detection. The point here is just that programmers make errors. Also that for crypto code, having the biggest set of eyes possible in open source scrutinize the code to try to find errors seems to be a very good idea. Okay, we're getting down to the real nitty-gritty now. Well, what about the operating system? That's others of millions of lines of code. I'm not going to say much about this except to note that there are ways people can tamper with your operating system, such as installing a keylogger. What a keylogger does is just record every keystroke that you type on your machine. So like your username and password for bank.com. This doesn't have anything to do with the web. It would break other things too, but it's still possible and affects your web browsing. And finally, the last layer I want to talk about is hardware. There is an interesting attack known as bad USB. What bad USB does is the following. You know those thumb drives that you share files with? You just plug them in and copy files from computer to computer. It turns out that you can reprogram the firmware, the software, burned into a thumb drive so that when you plug it in, it acts like a thumb drive, but it also does other things. Among those other things acts as a keyboard and just starts typing commands on your computer, which could lead to the installation of a keylogger, for example. These are all interconnected. One amusing anecdote about this is when I gave a talk at an NSA-sponsored conference in 2013, just before my talk, one of the hosts from the NSA, who's a very nice guy, came up to me and said, "Would you like a USB remote for giving your talk?" And I said, "I already have one keyboard, thanks very much." And he said, "I bought this at the store on the way in this morning, but I like the way you think." So, okay, that's all I want to say about the general background. We've actually gone through quite a lot of it. What I'm going to focus in on now is the web architecture and what's wrong with it and what we've done to try to fix it. Okay. So the main thing I'm talking to you about today is functionality versus privacy in web applications. So definitely the designers of the current web were thinking about providing privacy. They definitely were. But the way they designed the architecture of the web has led to this odd situation where there are certain kinds of really useful functionality that users want that the architecture of the web does not let developers build, at least in a straightforward, secure way. And what this forces to happen is the application developers then just come up with kind of wacky workarounds that compromise the user's privacy because the browser doesn't let them do things in a straightforward, secure way. What this leads to, in turn, is, if the user is even aware of the choice, sometimes they're not, the following choice. There's this shiny new web app that all my friends are using, and I really want to message them with this web app or whatever it is. But I'll have to give up my privacy because this was done in this privacy-violating way in the way it was implemented. Or no application, no fun, but I still get to have privacy. I think you know which one people choose in general today. So my claim in this talk, and the message I'd like you to take away from the talk, is that through careful design, it is possible to avoid this unpalatable trade-off in the web and in other systems too, although I'm just talking about the web today. We can, through careful computer science, system security research, design systems that allow web apps that give the user both rich functionality and user privacy. That's what I'm going to talk to you about. So why should you be concerned about privacy? Let's really get into the problem for web applications now. Well, the great success of web applications largely derives because it's so easy to build them. Why do I say that? Well, because web apps are the most open of open source. If you go to some website, all of the program for JavaScript for that website, at least for what happens in the browser side, is just there to be downloaded by the browser. So anybody can see it, and they can borrow from it and reuse from it. So this is good. It's really easy to reuse code. What this leads to is web apps that I'll call pastiches. You sort of cobble together bits of code you liked on other people's websites and build this thing held together with duct tape in the grand tradition of engineering. So a lot of that code's been written by other people. Now, why should you trust those other people? In particular, they could be malicious, right? Every site has code from lots of people. You probably have never met most of those people or have any idea who they are. The browser just runs the code when it downloads the code. So is it advisable to run programs presented to you by somebody you don't trust? Your browser does it every day, every minute, without asking you. So let's look at this more closely. In a single running browser, let's say a user visits different sites in different browser tabs. So here's an example, perhaps appropriately for our current venue in London, that I like to call bad weather. So you have a browser, which is one big piece of software, right? And on the left, you open a tab to look at your Barclays bank account. Things look like they're on a downward trend there. And on the right, you visit weather.com, which was obviously not taken today. And here's what you would worry about, right? You'd worry that weather.com might include some malicious JavaScript. Maybe they just borrowed it from some other site. They didn't even know. And what it's going to do is, since it's running in the same browser as the other tab, it's just going to read your bank stuff from the other tab and send it to, well, maybe weather.com. Maybe weather.com's the bad guy and just wants to know your bank information. So what's to stop weather.com from doing this if weather.com decides to? Well, today's web architecture actually does try to stop this from happening. Okay? And the way it does this is with what's called the same origin policy, or SOP for short. What the same origin policy says is that if weather.com goes ahead and puts a malicious script inside that wants to read from Barclays, the same origin policy says that the content in every tab, or for those of you who are web developers, in every iframe even, there's smaller granularity than a tab, is associated with an origin. The origin you can just think of as the domain name, like barclays.co.uk. This came from their origin. Similarly, weather.com is the origin. The same origin policy says a script that comes from one origin is simply not allowed to read any data that comes from another origin. Okay. So think of it as a brick wall between the tabs with different origins. So intuitively, we describe this, just to repeat because it's important. This prevents a script from one domain name from reading content from another domain name. And a computer scientist would say that this is a form of discretionary access control, which sometimes I call DAC for short. Okay. What's interesting about discretionary access control, so discretionary access control is you want to read something, either I let you and then it's yours and you can do whatever you want after that, or I don't let you and you can never get the data. That's what discretionary access control means. So the interesting thing about discretionary access control is that it is at once too permissive and too restrictive. Let me try to convince you why. It's too permissive because it turns out that if Barclays includes a script that some bad guy wrote that tries to leak bank information from Barclays' own users, but the script was taken from someone else, from somewhere else. If Barclays just includes it in its page, the browser will think that it's from the Barclays origin. So there's no different origin to save you. And it also turns out that browsers are allowed to send requests to any origin they want. So what this means is that if Barclays web developer borrows a malicious script and puts it in their page, that malicious script, if it's in Barclays' page, is free to read from Barclays' own page your bank information and send it to, say, evil.com. So it's too permissive. DAC is too permissive in this case. It doesn't prevent that. But it's also too restrictive at the same time. It like fails at opposite ends of the spectrum. So in the bottom example, let's say that you want to have an application that for some reason can read from multiple ones of your bank accounts. Perfectly reasonable thing to want to do. I'll say more about that later. So one bank account is at one domain name, the other is at another. The same origin policy says that if somebody wants to make a cool, useful app that wants to read from other origins, you're just not allowed. You're never allowed to read data from another origin, ever. And so this was meant to protect the user. The thought was, well, how do I know what's in the code from mint.com? Maybe it will just leak the data somewhere else. That's a good thought. but you also just can't build useful things. So to sum up, discretionary access control is too brittle. It means that you either completely cede control of the data or that you deny access utterly. And this means that it creates a challenge for getting privacy for the user, but functionality for the user. Okay, so let's say just a little more about Mint.com. Think about a financial dashboard app. So in the US, it's Mint.com. In the UK, it's actually called moneydashboard.com. I guess Mint was taken. It integrates and analyzes financial data from lots of different sites. So you want to see how much you're spending on coffee, on all your different credit cards. This application that runs on the web will tell you. Now, as I've already said, if they tried to write it in JavaScript, hosted at a domain name origin mint.com, that just won't work. The browser won't let the script make requests and read the results from HSBC and Chase. So this disallowing by the architecture of the web creates interesting consequences. On the privacy side, so we have this choice between privacy and functionality. On the privacy side, banks will not allow Mint.com to read their data, which means the user can't have an app. So we can have privacy and no functionality. On the functionality side, I guess if there were a way to override the same origin policy, which there actually is, but it's beyond the scope of this talk, banks could choose to give their data to Mint.com, but then Mint.com, the code, can violate the user's privacy and send the data anywhere. So in reality, how does Mint.com work, given that it can't be written in JavaScript? This is another scary part of the talk. Mint asks users for their bank login credentials. Just give us all your usernames and passwords. We'll store them. Thanks very much. And then pulls the bank's data onto Mint.com's server, logging in as you, integrates everything, and then sends you that page from Mint.com. By the way, Mint has over 10 million users. They've been bought by Intuit now. There is nothing malicious about this. This is just developers doing a good job trying to deliver functionality for users. So how are we going to solve this problem? The germ of the solution is confinement, which computer science is starting to have a little bit of gray hair. This is an old idea in computer science terms. Butler-Lamson proposed it in 1973. But it's been very elusive in practical systems. And the idea of confinement is extremely simple. It's we're going to let code we don't trust, that might be naughty, read sensitive data, but then we're going to prevent the untrusted code from leaking it. So what you'll say is you'll allow the script, the JavaScript from Mint.com to read Chase.com and HSBC.com, but the moment those reads have happened, you sort of put a wall around Mint.com and say you can't talk to anybody else on the internet anymore since you've read sensitive stuff. Okay? That's a high-level intuition. So we've built a system for the web called Cowell. There was an L at the end of that, Cowell, that does this. So it's confinement with web origin labels. And let me just quickly give you sort of a sketch of what it is. It provides confinement for JavaScript code in today's web browsers. What it does is it lets web app developers label data with the origin that deems that data sensitive. So think of it as a tag on the data. So for example, data sensitive to Chase, your Chase bank account data, could have the label chase.com. The data sensitive to both Chase and HSBC could be labeled the conjunction chase.com and hsbc.com. What data might that be? Well, after Mint does its work and integrates data from both of those sources, the result would be like that. Right? It would be sensitive to both those origins, combining data from them both. And then what you'll do is allow cross-origin sharing, but when a recipient of data that's labeled reads data with some label, sensitive to, say, foo.com, he will lose the ability to communicate with any other origin than foo.com. I've seen foo's sensitive data. I can still talk to foo because foo knows foo's sensitive data, but I can't talk to anyone else. How do you do this in Cowell? It's very, very simple. For Mint, once we've added Cowell to the browser, the Mint developer can just retrieve data from Chase and HSBC. That goes like this. The data that comes from Chase will be labeled chase.com. The The data that comes from HSBC will be labeled hsbc.com. Now at this point, the app for Mint has not read the data, it's just got the data, and what it can see is what the labels are. If it's willing to read, if it wants to read the data, it has to first, as we call it, raise its label, which means declare itself to be tainted by having seen things from that origin. So it will say, okay, now I've seen things from chase.com, which will immediately mean that Cowell in the browser will block all communication with hsbc.com since it does not equal chase.com. And then after the Mint app reads data from HSBC, it will lose the ability to talk to chase.com too. Okay? And that's it. This lets Mint read the statement data. It can now make you a pretty graph and show the dire coffee situation. And now Mint is confined. It gets you flexibility and privacy. So our design for Cowell emphasizes deployability. This is if you want your research to succeed in the real world, thinking about how it could be deployed is hard, but important. And we don't know if we're going to succeed on deployability, but we tried. Here's how we tried. We built full implementations for two of the most popular browsers that we could get the source code for, Firefox and Chromium. And we've released in October 2014 Cowell as full open source, as well as a runnable binary that you can just download and run a browser with Cowell baked in. It's simple. Cowell just has 3 new JavaScript primitives, 3 new sort of commands to learn in JavaScript if you want to use it in your web application. It also uses origins, which web developers already knew about, to express policies. So we think web developers will be familiar with the underlying concepts. It's fast. The worst case page load time increase. In other words, when you visit a page, how much longer with Cowell running does it take for the page to finish loading? In the worst case in our experiments, it took 16 milliseconds longer. So fairly acceptable to users in increased latency. And it's backward compatible with legacy web pages. Telling people that your security system requires rewriting every web page on the internet as a starting point is not very good for deployability. That is a problem we do not have. You opt in to use Cowell on your site. So that's most of what I want to say about Cowell. I will say that there's been some gratifying early interest from the technical press in the system. We got written up in Network World, got written up in Engadget, and somewhat fearfully when we first heard it was going to happen, but it did turn out they were nice, we got written up in the Register as well. So you can check out some of that if you'd like. So to wrap up, the web really invites reuse of code from people you don't know and shouldn't trust. And this creates privacy risks because untrusted code in an application could leak the user's sensitive information to some miscreant somewhere. And the status quo web architecture with the same origin policy, which is a form of discretionary access control, can force developers to have this awful choice between functionality and privacy. Do I use the app all my friends are and give up privacy, or do I not get to use the app? Cowell lets you have both functionality and privacy. We're actually in discussions. Dan Stefan, the lead PhD student on this project at Stanford, is discussing Cowell with the W3C, the World Wide Web Consortium standards body, which sets the standards for how browsers and web servers work. So we're hopeful we may be able to get some of Cowell out there and really used by the broad world. And give it a try. If you go to cowl.ws, you can download a ready-to-run browser with Cowell in it. If you are a web developer by any chance, we have a bunch of examples on the site showing you exactly how to use Cowell, and you can try it out, and we welcome feedback from the community. I'll stop there and welcome any questions.
Thank you, Brad, for a really fascinating but slightly disquieting presentation. And so we have time for some questions, and I have one person lined up already. Could you wait until the microphone comes in, please?
Thank you. All right, I'll try not to deafen everybody. So I don't know if this is very easy for you to give me much perspective, and it's rather, not the core of your talk, but in cases where people are, for example, writing malicious JavaScript with the intention that it might be copied to another location where it's going to report back and send information to some location, How common is that? I mean, I'd be very interested.
That's a great question. So the question is sort of, are people really doing this today? Have we found examples? We've looked a little bit. We haven't looked a lot. What I can tell you is two things. I actually had a slide on it, but I deleted it. There's a JavaScript library called jQuery that you may have heard of. And it turns out that about 70% of the most popular websites all include it in their pages. It turns out that in late 2014, the site for jQuery.org, the people who put out jQuery, was hacked. They did not tamper with the library, but it's possible they could have, the attackers. So we think that that's evidence that this sort of thing could start to happen. Another thing I'll say is that something else that's written in JavaScript is browser extensions. And I've done other work with Peter Marchenko, my student, on browser extensions, and we found all kinds of nasty things in browser extensions, like browser extensions that show you your vCards and then send a copy of the contents of the vCard to someone somewhere else on the internet when they show you a vCard. So we do think that malicious JavaScript is a phenomenon that we could start to see more, even though we haven't seen huge numbers of instances of it so far.
We have a gentleman at the back.
Just a quick question about how that Mint example worked. So as a user, I've logged into Mint, or I'm on the Mint website. How does it then get my HSBC details? Is it because I've logged in on the HSB web?
This is an excellent question. So the question is, well, what I said was that the problem with the workaround version of Mint is that I have to give away my credentials. Don't we have to do that too? That's a sort of more, you were much nicer in the way you asked the question. I'm not saying you were suggesting that. We don't have to have Mint know the credentials at all. And the reason is exactly what you said, that if the user opens other tabs on the other sites and exposes their credentials only to those sites, which of course the user trusts those sites, then because of Cowell, Cowell will allow the relaxation of the same origin policy with confinement and let the code in the Mint tab read the data that's already there in the other two tabs.
So when you say it isn't then allowed to send it on, could it not embed it in a form in its own page and submit the form on the other?
So I think what you're talking about is what's called a self-exfiltration attack. This is something known to the computer system security community. What this has to do with is that sometimes there can be a vulnerability in a script where an attacker can cause a script to send something to the same site that the script came from. Just to be clear, the script for Mint.com loses the ability to communicate with Mint.com also once it's read data from HSBC or Chase, because Mint.com is different than those labels.
So the data will just stay in the browser in that one
Exactly.
screen. So you still lose some functionality. So once you basically get a picture that you can then, there's limited interaction after that point?
With Mint.com?
Yeah.
Yeah, it's a great question. So the question is, what happens after the script for Mint's application can't talk to Mint anymore? Sounds like we're sort of dead. And so our observation is that for many, many applications, there's a period where the script needs to communicate with its own site. But because the browser is so richly featureful in HTML5 and JavaScript, there comes a point where you sort of got the environment you need in the browser tab for Mint, and it's okay to cut the cord to Mint.com. Our observation, we've looked at, so we published a paper in October 2014 that if you just Google Cowell and my name, you'll find it. We actually have a taxonomy of a wide range of applications where this idiom works perfectly fine. So it's a great question. I'm sure there are applications where it could be a bit of a challenge where you need to be chattier with Mint.com server, but we have a story in the paper, a true story in the paper, about what you can do in that case as well.
Okay.
Tiny.
No, I'm sorry. Could perhaps we can, I've got time for one last question. And lady here.
This is so fundamental and so basic and idiotic compared with all those. I've never been much interested till this moment in the internet. How could I start even to put my toes in the water of learning this? Because you've absolutely fascinated me. I've got lots of qualifications elsewhere. I'm not a fool. I mean, I'm a human rights barrister, but this is so interesting. How would I start? Where would I go?
So just to clarify the question, you're interested in investigating privacy issues in the internet, or you're interested in using the internet more?
Well,
or less.
This is so deep, but it does sound so interesting. I don't think I'd be able to plunge straight into this. So how would you begin to...
Questions of privacy in the internet, investigating questions of privacy in the internet. So one thing I would say is that Harvard University has a center called the Berkman Center for Public Policy that focuses on internet-related policy things, and it has people from law, people from public policy, and people from technology. And they put out a number of, well, everything from books to papers, briefings on issues in this space, and they're written for a broad audience. So that's a good place. Oxford has an Internet Institute also, I believe. I think UCL's graduate Ian Brown is there, and he does a lot of work in the sort of privacy and policy space. I think he was involved in some interesting court cases about internet privacy recently in the UK, actually.
At this point, I think that we need to close the discussion because there's another class that are going to come in. Could I please ask you, on your way out, if you could complete the survey form and hand it to the stewards on the way out? And to remind you that there will be another lunchtime lecture next Tuesday. And thank you again, Brad.